Welcome to The Explainer. So today we're going to tackle a question, a really big one, that sits right at the heart of modern engineering. And honestly, it's getting more critical every single day.
So let's just dive right in. I want you to think for a second about all the crazy complex systems we rely on every day. Power grids, airplanes, self-driving cars, the whole shebang. The big question is this: how do we know for sure that they're safe? Not after they're built, but right from the very beginning, when they're still just ideas on a drawing board.
Well, it turns out the answer lies in this really powerful idea. It's like a universal blueprint for all of these different systems, a kind of common language that lets engineers talk about and understand any dynamic system, no matter what it is.
And it's got a name: Axiomatic Systems Theory, or AST for short. So what is it? At its core, it's a really rigorous mathematical foundation. Think of it as that universal language we were just talking about. It gives us the tools to understand, to predict, and ultimately to control how these super complex systems behave, all in a really powerful, abstract way. Okay, here's a great way to think about it. Imagine building a massive skyscraper. That's our complex system, right? Well, Axiomatic Systems Theory, that's your building code. It's the set of foundational blueprints that everyone agrees on, the rules that make sure your skyscraper won't just fall over.
And this is the key difference, right here. We're not talking about calculating the specific force on one single steel beam. That's quantitative. AST is all about the principles. It's qualitative. It's about defining what stability even means for any building, ensuring the whole design is conceptually solid from the get-go.
Okay, so let's dig into that a little more. How does this blueprint actually let us stress test a design? And I mean stress testing it purely on paper, way before a single screw is turned or any hardware is built.
Well, AST helps us answer these really fundamental questions about how a system will behave. By defining everything in this abstract mathematical way, we get to ask things like, hey, if we give this system a good push, is it going to fly apart into a million pieces? Or will it settle back down into a safe, stable state? These are the kinds of questions you need to answer.
So what we're really talking about here is a kind of formal safety checklist. We can use the math to prove things like, will the system stay within safe limits? Does it naturally lose energy instead of building it up to dangerous levels? It's all about guaranteeing right from the start that the design is solid and won't just collapse under pressure.
But, being safe and stable is only half the story, right? It's great if your skyscraper doesn't fall down, but what if the elevators don't work? The system also has to actually do its job.
And that brings us to our first big idea here: controllability. It sounds complex, but it boils down to a really simple question. Can we actually steer this thing? Can we get it to go from where it is to where we want it to be? Do we have the controls to make it do what we need it to do?
Let's go back to our skyscraper. Controllability is basically making sure the elevators can get to every single floor. I mean, what's the point of a penthouse if you can't get the elevator to go there, right? If it only goes to floors 5 through 10, you have a major controllability problem.
All right, so the second critical piece of the puzzle is something called observability. And this is all about knowing what's going on inside the system. Can we figure out what's happening internally just by looking at the outputs, the stuff we can actually see and measure on the outside?
So back to the skyscraper, observability is like your security system. Can your cameras actually see all the critical hallways and doors? If you've got a massive blind spot where you can't see what's happening, you don't have a clear picture of your building's security. You lack observability.
Okay, so we've talked about all these abstract ideas: blueprints, stability, controllability. But what's the big takeaway? Why does any of this matter in the real world?
Well, this is how it all ties together. You start by defining those universal rules, the building codes. Then you check your abstract design against those rules. And if it all checks out, you can formally prove that the final, real-world system is going to behave exactly the way you designed it to. That's how you build trust.
So at the end of the day, what's the bottom line? This language of systems, this AST, it's not just some academic exercise. It's the invisible foundation that makes pretty much all of our modern complex tech possible. And more importantly, safe. It's the reason we can even begin to trust the automated systems that are shaping our world.
And that leaves us with one last kind of big thought to chew on. As our world gets more and more automated, and as things like AI become exponentially more complex and, well, autonomous, what new blueprints are we going to need? What are the new fundamental rules we'll have to invent to make sure that the future we're building is one we can actually understand and truly, deeply trust?